Thanks for having me here. I am from Center for Brain Research, which is an autonomous center at Indian Institute of Science. Since we were speaking of data sharing, data acquisition, there's one thing I wanted to tell you. There are two very big projects happening at CBR, Center for Brain Research. We have recruited a cohort of 10,000 people in a village near Bangalore called Srinivasapura. It's a village of farmers, mango farmers. They are assessed longitudinally, that is every 2 years or so, they are brought to the center. Clinical assessments are done, their EEG, structural MRI, functional MRI, diffusion MRI, they are all acquired. So it's a very ambitious study. They want to see how neurodegeneration sets in, how the decline really happens. So it's a huge wealth of data that's about to come out from this center. Yeah. So today I think I took the title of the session very, very seriously. So I only focused on explainable AI, unlike the other speakers here. This is the outline of my talk. We will have a look at what the recent paradigms are in analyzing MR images. And I picked up two case studies that are inching towards explainable MRI, explainable AI in MRI. Yeah. We all know the biggest buzzword in machine learning today is deep learning, right? So successful. So what you're seeing here is one example of UNet. I think it was proposed in 2015, and even till this day, there are several variations of UNet coming up. So what we are seeing here is, I think, from the BRATS data set, lots of tumors. So you see the first image here, where you get to see the tumor, the annotated one where the label is shown, not just the tumor, even the subregions in the tumor in different colors. And then the performance of UNet. And at the very end, it's a variation of UNet. So there are hundreds of such variations that are trying to make the results better and better. So the goal is to try to capture every serrated part of the boundary. You want to distinguish the regions as close to the ground truth as possible. So this is way back in 2015, and even now there are several variations of UNet coming up. So that's the kind of interest that it has generated. Now, what is so good about this paradigm? It is data driven. There is no necessity for me to handcraft features. You don't need to know what is important in able to segment out the tumor. The patterns could be unknown. There is no uniformity in shape, size. It can sit wherever in the brain, right? So there is no known pattern. And it's so important to be able to deal with this because we know the kind of diversity there is across people, across races. There is no need for pre-processing. It means I don't have to tamper the image at all, except for maybe size uniformity, which means I don't have to worry about the histogram, I don't have to worry about the brightness, I don't have to worry about any other adjustments, which is key when you deal with medical images, because you don't want to tamper it and manipulate any small detail. So you want to do it without any pre-processing, which is what this paradigm allows. It's not moving to the next. Just and there are some scenarios where it's not easy to build analytical models. So people who do MR imaging know that motion is a very big cause of artifact. So what we are seeing here is a comparison of the motion corrupted image on which no diagnosis can be done. And there you have the motion corrected image on which a radiologist can work. And to do this without a setting like deep learning is very, very hard. Why is it? Because you first have to model what kind of motion happened and then undo that that motion and then create your motion corrected image. So this is easily done using deep learning. It's a very recent result. Now this kind of a thing is a very big problem, especially when you're dealing with very young patients or very old patients who cannot be still. And there can be some disorders where keeping still itself is hard. Essential tremors, Parkinson's, there is this involuntary motion happening all the time. But then deep learning comes with its own challenges. So this is a comparison of heat maps for Alzheimer's disease detection. We know that the solution of this, the deep learning model solution is black box in nature. No one knows what's happening inside. So you try to explain out the results. You use class activation maps. They use CNN fixations. They use frameworks such as LIME, SHAP, but they all work in retrospect. Once you've got the classification label, you try to explain out what has resulted in that, right? You cannot use it in the forward pass. And we know that, for instance, in Alzheimer's, there are multiple changes of very varied orders. For example, you see these enlargement of ventricles, very different in normal, very different in AD. And then there is shrinkage of cerebral cortex. So some changes may be subtle, some changes may be very blatant, but how do you capture them all? When you look at the class activation maps that deep learning gives you, it latches on to very little, right? So if at all relevant aspects of the changes are captured, it's a very small subset. You don't get to see all the different changes between the classes. And some more challenges very specific to MR imaging. So these are MR images of the same subject taken across different scanners. The manifestation is so different. So if you fixate on one specific region, I tried to mark one with the red arrow. They show up very differently in different scanners, which means there's a whole lot of diversity in the kind of images you're trying to analyze. Another very important aspect in deep learning is, do you see what's happening here? The panda image is given the label panda with about 57% confidence, and what they've done to it is added some tailored noise. It doesn't perceptibly change the image at all. There's very little change that's happening, but what is the result? The classifier gives it a very wrong label and with a very high confidence. So this is called adversarial attack. So you decide to tamper a particular label, you can come up with a structure of noise that will change it. And we know we cannot afford to do this in healthcare. So clearly what is missing in all this is explainability. There is great performance, no doubt, but the trust factor is missing. So I picked up two case studies that try to work towards explainability. One is on schizophrenia and the other is on AD. We'll first look at causal network analysis in schizophrenia. So this is the paper that I picked up, a 2018 paper. Here the objective was to investigate temporal and causal relationships of structural changes. Now, when we study causal modeling, like the speakers before me spoke of, the most desired kind of causal modeling would be where counterfactuals can be answered, as the first talk of the morning said. But a very primitive way of analyzing causality uses what is called Granger causality. And this has been used across domains. It has been used in finance, stock markets, weather prediction. So what Granger causality essentially speaks of is, let's say we are observing two variables, x1 and x2. So we model x1 as lags of x1 plus lags of x2. So this modeling definitely gives rise to some error. So let's say it is some E1. I do the same thing with x2. x2 is written as combination of lags of x1 and lags of x2, and there is some other error E2. So in this there is no assumption at all. I assume that x1 comes from x1 and x2, x2 is also coming from x1 and x2. Now what is Granger causality about? I want to see whether x1 is influencing x2 or is x2 influencing x1. So which way is it flowing? So just look at the top panel. Here I am expressing x1 as only a combination of lags of x1. Whereas on the other side, I am expressing x1 as combination of lags of x1 as well as lags of x2. So in both the modeling, let's say in the first case my error is E1 dash, in the second case it is E1 double dash. So this error will tell me which of them is true. How? If indeed x2 is Granger causing x1, then the variance of E1 double dash will be less than the error in variance of E1 dash. So this is one way of finding out whether x2 is making a difference to x1. Is there some sort of causality? Now you will see the same thing replicated here the other way. So what in English, in words, what is it trying to do? Can I predict x2 using the information available till that time? Is this any different from using information from lags of x1? So this is what we are trying to capture using those two equations. It's a very, very primitive form of trying to have causality in our modeling. Now this also gave rise to some very good results. So they could show the progression of the disease. Starts where, progresses where, and then spreads where all. So this is one way of trying to get in explainability in our modeling. Yet another way is by studying the shape of the data. So here they use topological data analysis. So one specific branch of topological data analysis is called persistent homology, and this has been very effective in Alzheimer's. Let's see what we mean by shape of data. We are given some data in some feature space. You visualize them as a point cloud. It can be along a straight line. It can be along the circumference of a circle. So we don't know on which manifold this data is coming from, right? So we have no clue. So when we do not have any assumptions, we don't have any clue. It could be easily describable or may not. But what is it that we intend to do? We want to extract shape features from the data, topological features. What do we mean by that? Now, why bother with shape of data? Because data samples from a specific phenomenon typically lie on a local manifold. So the feature space may be very vast, but our samples are coming from a very localized subspace. So for instance, manifold of Indian faces occupy a very different part of the feature space compared to, let's say, African faces, European faces. The same thing with MR images. So manifold of healthy MR brain scans are very different from the manifold of unhealthy MR brain scans. Now what do we mean by topologically similar? It is very counterintuitive to what is geometrically similar. So in topology, you said two objects are the same if you can deform one into another without tearing or cutting. Let's see what this means. A cup with a handle is topologically similar to a donut. Now this is not very intuitive unless we see these. So what all can I do to the cup with the handle to deform it all the way to make it a donut? A ball, a sphere rather, is topologically similar to a wine cup because I can bend, squeeze appropriately and interchange between these two shapes. whereas a cup with a handle is topologically similar to a donut. So this is very different from what we think is intuitively similar, geometrically similar. Now what is it that we are given? All we have is a scatter of points. So how do we get shape out of this? Now some basic building blocks. You think of points as zero-dimensional simplex. You think of straight lines or edges as one-dimensional simplex. You think of triangular faces as two-dimensional simplex. You think of tetrahedrons as three-dimensional simplex, and so on. So we will utilize all these basic building blocks in describing shape. So we start with the set of points. Now what do? We want to build a simplicial complex. And how do we do that? I don't know if it's visible. Around every point that you have, you start building a ball of a certain radius. Now for very small values of this radius, there is no intersection between circles, right? Nothing is happening. But when you increase the radius some more, you will see that certain balls start overlapping. And when balls overlap, you connect the points, right? Here it is very neat. So every point has two adjacent points whose balls are intersecting. So now you have connections between points. Do we stop here? No. You will increase the radius some more, and now you will see balls from multiple points are now intersecting. Not just two, there can be three or more. And then you connect them some more. So you are building some structure here. So when you gradually do this, at one point, all points are connected, right? At one value of the radius, all points get connected. So this is when we say you've built a simplicial complex. So what we have done in this is we have gradually built a nesting structure. We started with disjoint points, and then some points got connected with edges, and then some more got connected using triangular faces, and then tetrahedrons, and so on. So this nesting structure allows you to use group theory, that is matrix algebra, to determine the shape descriptors. We'll come there. And this nesting structure is very important. So at each level, it is totally contained in the next level, and so on. So we have inductively built higher order simplices from lower dimensional simplices. So here we will use the notion of Betti descriptors to describe shapes. So Betti descriptor is like a vector. Given a shape, it's a vector that counts something. So what does it count? It counts the number of d-dimensional holes. So the dth number will count the number of d-dimensional holes. For example, here the point, when you look at beta naught counts the number of connected components. So a point is a single connected component, so beta naught is 1. It has no one-dimensional holes, it has no two-dimensional holes, so it's all 0. So the description of a point is 1, 0, 0. Now let's look at the cube and the sphere. Do you notice this in the table? They both have the same representation. It means cube and sphere are topologically similar. Do we see how this can be? It's very different from the donut. So donut has value 2 for beta 1, which means it has two one-dimensional holes and it has one void. Do we see how sphere and the donut are so different topologically? The sphere is a single connected component, so is the donut. Till there we are all fine, right? The cube encloses one space, one volume inside. The donut also encloses volume inside. So beta 2 is 1 and 1. What about beta 1? Why is it 2 for the donut and 0 for the sphere? So I can put my finger through the donut, right? So that counts as one hole, and I can put two fingers around the donut, like this, the way I would, if I had to hang it as a decoration, right? So that gives the value 2 to beta 1. So what is intuitively similar is very different from what is topologically similar. Now, how do we use this idea? So we started with points, we moved on to building connecting edges, and then we connected them with triangles, and then we connected them with tetrahedrons and so on. So over the scales, what we did by increasing the radius of the balls is called filtration. So over the scales, the Betty descriptor beta 1, which was earlier 0, right? There were no holes first. At some scale, beta 1 becomes non-zero. That happens here, which means beta 1 is non-zero, and it stays that way for a long, long time. And only after a certain other value of the radius, it goes back to 0. So we came up with a descriptor that survived a large number of scales. So that is what persistent homology is all about. Now, because of this, you will say that this set of points has the description where beta 1 is 1. So the shape of this data cloud is represented as the Betty descriptor 1, shape with a single 1D hole. How is this used in Alzheimer's? So this is a McKay paper of 2021. They looked at the structural images of a normal brain, aging brain, and AD brain. So these are the observations, that both aging and AD result in loss of white matter volume and thinning of gray matter. And gray matter of aging brain breaks down into smaller connected components. So this can be used to describe using Betty numbers. A comparison of white matter with Alzheimer's and without. You see this enlargement of ventricles, right? So there are so many topological differences between the two groups. So here's a plot of the Betty number across different scales. So this is Betty number 0, Betty number 1. So Betty number 0, there is appreciable difference between young and old population, right? So some discriminators are better than the other. For example, here also there is a difference, but not as pronounced as for Betty 0. So this is a comparison of the Betty curve for the young population, an aged brain, and AD brain. There's a big difference between the three groups. So this can be used for classification. So here you can interpret the numbers that you are seeing, making it more reliable. Their results were fairly good. They compared it with CNNs because that is what they were fighting. So in summary, explainable AI is crucial for analyzing MR images. So some solutions towards that could be causal modeling, persistent homology. We see that the advantages here compared to the deep learning paradigm, you don't need data augmentation, you don't need large annotated data sets, and it's quite robust to variations and noise. These are my references. I'll be very happy to answer questions if any. Thank you.
Long live India and France friendship.